In this video, we shall try to understand the phenomena of diffraction of light. So what is diffraction? Let's assume you have a slit, as shown here. The size of that slit, it's about 0.3 millimeter, let's say. So it's a very tiny slit. Suppose you have light wave fronts hitting the slit like that. So the direction of light is like that, and it's hitting the slit directly. Upon passing through the slit, the light bends from a straight line path and enters the region that would otherwise be overshadowed, like that. And the direction of travel can be represented like that. So this spreading out of light from its initial line of travel is called diffraction. We will be able to pick up the effects of this diffraction if we place a screen right there. Such a setup is known as the single slit diffraction. And this is what we are interested in today. In general, of course, diffraction occurs when light waves pass through small openings, around obstacles, or by sharp edges. Here we are interested in small openings in the form of a single slit. Let's look at the setup more closely. In this diagram, I'm going to exaggerate the scale so that small slit would appear slightly bigger just to make a point. The width of that slit is taken to be A. And this is the screen on which the effects can be seen. As a first step, I'm going to divide this slit into two equal segments like that. So this is the central line. So that width is A over 2 and this is A over 2 respectively. Now let's assume a ray of light hitting that slit like that. Let's look at two particular rays. One ray is hitting the screen like that, and the other one is hitting the screen from the central part of that slit. These two rays, let's label them 1 and 2, will travel different distances as they reach that point. The difference in the length or the distance they traveled is given by that distance right there. If we take this angle to be theta, what we have is a right angle triangle. So this is 90 degrees. That angle here is theta. It can be shown to be the same theta as that one. So this distance we call the difference in the path length between these two rays. Delta is quite simply A over 2 sine theta. So when this difference in path length equals to half the wavelength, meaning the maximum of the wave 1 meets the minimum of wave 2, they interfere destructively to give a dark spot there. So equating this result to that result, you get A over 2 sine theta equals lambda over 2. The 2 goes away. So sine theta equals lambda over A. And this represents a condition for a dark spot to occur at that angular position. The action of splitting the slit into two equal segments is not unique, meaning we can split it into 4 equal segments. Each has a width of A over 4. If this were to be the case, let's analyze two light rays, light ray 1 and light ray 2, hitting a spot on the screen like that. And there still will be a difference in the path they travel in terms of distance. And the difference in the length they travel can still be represented by such a right angle triangle. The only difference now, the difference in the path length delta, will no longer be A over 2 sine theta, because this distance is A over 4, so delta will be A over 4 sine theta. Equating this to the fact that if the phase difference between these two rays, 1 and 2, is half the wavelength, then we get A over 4 sine theta equals lambda over 2, you see that sine theta will turn out to be 2 lambda over a, which is also a condition for a destructive interference to occur there, namely a dark spot to occur there. Generalizing this treatment, we can further divide this slit into 6 segments, 8 segments, and so on, and the effect it would have on this final equation is the integer 2 must be substituted with an integer m, where m could be plus minus 1, plus minus 2, and so on and so forth. So this theta is theta m accordingly, namely this angle here is theta m. The lateral position, namely this length, let's call it ym. If the distance between the slit and the screen is L, then if L is much larger than ym, we see that sine theta m is approximately the same as tangent theta m, and tangent theta m is ym over L. So equating this to that result, we get a formula that enables us to pinpoint the lateral position of any dark points on the screen. Quite simply, it is m lambda over a L. We note m cannot be 0. M can only be plus minus 1, plus minus 2, plus minus 3, and so on. M can never be 0 because the central position here is always bright. It is not a dark spot. It's always a bright spot. So what is the effect that is observable on the screen? You will observe a central bright followed by a dark spot and then the second bright on either side like that. And this brightness, as you move away from the center, it will fall in intensity like that. So the positions of the dark spot that we point out earlier using equations is that, and symmetrically here, here, and there, in between bright spots. So that is called y1, this is called y2, y3, this is y minus 1, y minus 2, y minus 3. All these are symmetrically situated about the central bright. This pattern can be diagrammatically represented using a curve or graph. So that's a central bright, you have a peak there, and then it gets to a minimum, and then you have another smaller peak like that, minimum, smaller peak, and so on, and the intensity of the successive peaks will just die off. So if you want to determine the width of the central bright, you need to determine that distance. If this is y1, this is y minus 1, all you have to do is to take y1 plus y minus 1, and since these are the same, it is quite simply 2y1 or 2y minus 1. That would give you the width of the central bright. If you want to determine the width of the next bright pattern, so since this is y1 and that is y2, so the width of the next central pattern is quite simply y2 minus y1, and so on. Let's look at the following problem to see how to do just that. Red light with wavelength 630 nanometer passes through a slit 0.28 millimeter wide. The diffraction pattern is observed on a screen 4 meters away. What is the width of the central bright fringe? Remember the equation that we wrote down a few minutes ago? Ym, the lateral distance of dark spot, is given by m lambda L over A. So this is the distance between the slit and the screen. This is the size or the width of the slit itself. This is the wavelength of the light used, and this is the order of that dark spot. So the central max in this diffraction pattern would look something like that. So this is the 0 position. So this is y1 and this is y minus 1 because this is where you have dark spots. So to determine the width of the central fringe, meaning that distance, let's call it delta. Delta is quite simply y1 plus y minus 1 or 2 times y1. So 2 times y1 is 2 times m is 1 lambda L over A. So that is 2 times lambda is 630 nanometer. So let's convert that into meter, 10 to the power minus 9. L is 4, that's that one right there, over the width of the slit, 0.28 millimeter. So 0.28 times 10 to the power minus 3. And this will give you the answer in meter. And the calculation reveals the answer to be 0.018 meter, or quite simply 18 millimeter for part A. Part B, calculate the width of the first bright fringe on either side of the central bright fringe. So that means the width of the next bright fringe after the central bright, that one. So what is that distance? So now we know this is y1, so that has got to be y2 because that's where the third bright fringe occurs. And the same thing occurs on the other side. That's the second bright and this is the third bright. So it's sufficient for us just to consider one side. So let's look at the top one. So this width, let's call it delta, is given by y2 minus y1. Now y sub m is given by this expression. So 2 lambda L over A minus lambda L over A is a lambda L over A. So that is your delta. So let's substitute the numbers. The wavelength is again 630 nanometers, so times 10 to the power minus 9. L is 4 meters. That is the distance between the slit and the screen. The size of the slit is 0.28 millimeter. So 0.28 times 10 to the power minus 3 to convert that into meter. And the answer will be 9 times 10 to the power minus 3 meter, or 9 millimeters. And that solves the problem. Thank you for watching.